So we discuss a few more properties about associated primes in this lecture. So here is a proposition. Let R be Noetherian and M finitely generated, then the set of zero divisors on M is the union of the associated primes. Primes of M. What are we saying? So what is a zero divisor? So R in R is a zero divisor. So this is zero divisor on M if there exists an x not equal to 0 inside M such that Rx is 0. Okay. So what we want to show is that every such R belongs to an associated prime, to some associated prime, and conversely, every element of an associated prime is a zero divisor. Okay, so proof of proposition. Okay, so let P be associated to M. This implies that there exists X in M such that annihilator of X is equal to P. Okay. And if annihilator of an element is a proper ideal, then it must be a non-zero X. Okay. So this implies that every element of P is a zero divisor. Okay. Therefore, the union of P union over P, where P runs over the set of associated primes, is consists of zero divisors and nothing else. Okay. So now, conversely, let R in R be a zero divisor. Okay. Let X not equal to 0 inside M be such that Rx is 0. So now consider the set annihilator of X in R. Okay. So now this is an element. Okay. So among elements maximal among annihilators of arbitrary y in M are associated to M. They are in that set as M. Okay. So now consider, let lambda be the set of all things of this form. Okay. Y is non-zero, and Y contains this ideal, this. Okay. This is non-empty because this annihilator of X itself is inside here. R is Noetherian, so lambda has a maximal element. Lambda is non-empty, so lambda has a maximal element, which means that annihilator of R of X is inside P for some associated prime. Associated prime P. Because the maximal, so this is a collection of ideals. Clearly with y equals x, one can get that belongs to the set, so this is non-empty, and therefore maximal among them, maximal among ideals of this form, they are associated and they will be inside P. Okay. So now actually we can make this a little bit stronger. So this is about annihilator of a single. So what did this argument say using Noetherian condition? That annihilator of an element is inside some associated prime. We can actually prove a slightly stronger statement, which is that if I is an ideal that consists of 0 divisors, then I is in some associated prime. Okay. I mean, it will have to use this proposition and one more proposition called prime avoidance lemma. Okay. So here is it's a statement about arbitrary rings. Okay. Let P1 through Pn be prime ideals. Let I be an ideal such that I is in the union of the Pi. I is in the union. So the union itself is not an ideal or may not be an ideal. So I is inside here. Then I is inside Pi for some I. Okay. And this is not the most general version of this lemma. This lemma. One can relax these conditions. So I will put them as exercises. But this is the version that we would need to use. Okay, so we will just. Okay, so why is it called prime avoidance? It says that if prime avoidance is usually the contrapositive statement, which is that if I avoids each of the Pi, I is not a subset of each of the Pi, then I is not a subset of the union. Okay, so that's some ways. Sometimes that's how it's used. Okay, so that's why it's called prime avoidance lemma. So proof. Okay. So I is contained in the union of n primes, and we want to show that I is none of them. So we can assume that. So we'll proceed by induction. Induction on n. Okay. And we can assume that I is not contained. If n is 1, there is nothing to prove. Okay. So if n is equal to 2 is what we have to check. And so what do we? So we assume by induction that I is not contained in a union of fewer than n elements in P1 through Pn. Because if that were the case, then by induction we would know this, so we can assume that it's not contained in any. So what happens when n is equal to 2? Okay. So what is the hypothesis? The hypothesis is that I is contained in the union of is in P1 union P2, and we want to show that I is in P1 or I is in P2. Okay. So since I is not contained in the union of n minus 1 things here, okay, before we start, we can even set up that notation. Okay. Pick xi in I, but not in the union of Pj, j different from I. Okay. So since I is not contained in the union, we can pick such xi. Okay. Now what does it mean when n is 2? Okay. So xi, x1 is inside I, but not in the union of things that is different from I. So it is in P, it's in I but not in P2. X2 is inside I but not in P1. I is contained inside P1 union P2. So what about x1 plus x2? Okay, sorry, before we go into x1 plus x2, what does this say now? X1 is inside I but not in P2. Therefore, and it is inside P1 union P2. So now this one says x1 is inside P1, x2 is inside P2. Okay. Okay. Suppose x1 plus x2 is inside P1. Okay. So x is inside P1. X is in, so we have to show. Let's so suppose here look, x1 is inside I1 inside I but not in P2. It is inside P1. So x1 suppose x1 plus x2 is inside P1. So putting these two conditions, we would get that x2 is inside P1, which is a contradiction. Therefore, x1 plus x2 is not inside P1. Okay. Similarly, x1 plus x2 is not inside P2. Okay. So, what is the conclusion? The conclusion is that if I is not inside P1 and P2, I is not in the union. Okay. So x1 plus x2 is not inside P1 union P2. Okay. So this is inside I. Okay. So this is the conclusion. And one observation that we would like to make at this point is that, which is not relevant for this proof, but it is relevant for an exercise, is that we did not use the fact that P is a prime here. That Pi is prime. Okay, so the first two ideals in that list, P1 and P2, need not be prime ideals. Okay, so that's the observation that we take from this, which is relevant for one of the exercises. Okay, so now assume n is greater than or equal to 3. So then we consider the element. So we have picked elements x1 through xn satisfying this, and consider the element x1 plus x2. So x2 plus x times x3 and so on up to xn. So this element, this is inside P1 union Pn. That was the hypothesis. This is an element of I. Okay. So if you assume that since x is not in P2 union Pn, if I is not in P2 union Pn, we will get that. So I2, we can assume, that's by induction, is not a subset of P2 union Pn. Okay. And from this we will get so x2. X2 is not inside x2 is inside I, but not in the union of every element which is different from j different from 2. Okay. So then so from this, therefore, arguing that one gets that x2 x1 is inside P1. Okay, and from which is a contradiction, because we started off by saying pick an x1 that's inside I, but not in the union. Sorry, not x1. I apologize. This will prove that x2 through x3 up to xn minus 1 xn is inside P1. Okay, so these elements were picked inside I, but avoiding everything other than second, then avoiding everything other than third, and so on. So these elements are not inside P1, but their product is inside P1. But P1 is a prime, which is a prime. Okay, so note that xi is not inside P1 for all I different from 1. Okay, so this is a contradiction. So that's the proof of this prime avoidance lemma. And using these things, we can get the following corollary: R-Noetherian I, an ideal of 0 divisors, okay, not necessarily killing the same x inside M. Okay, 0 divisors on M. M is finitely generated. Okay, it doesn't mean I is a subset of the annihilator of some element. It could be annihilators of various elements. Okay, then there exists an x not equal to 0 in M such that Ix 0. We are not assuming that. It just says that for every element inside I, every element R inside I, there is an x such that Rx is 0. That's all that we are assuming here. But we are saying, we are switching the order of the quantifiers here. There exists a 0, there exists an x such that Rx is 0 for every element. Okay? So the proof is just using prime avoidance. Notice that I is in the union. I is in the union of P associated to M. This is a finite set, so this now implies that P is inside. This is prime avoidance. I is subset of P for some P in associated to M, but P itself is an annihilator of some element, so I annihilates the same element. Okay, so that's the end of this statement. Okay, so another useful proposition in this topic is the following. Let's say R is not R-Noetherian, M finitely generated. Then there exists a filtration 0, which we start at 0, M1, and an increasing filtration like this. Of course, R is Noetherian. These are submodules of M, so this is not going to go very far. It's going to stabilize somewhere, but we can actually do this. We can get such a filtration, and this is some MR equals M, such that Mi mod Mi minus 1 is isomorphic to R mod Pi for some I. Okay, so at successive stages, the quotients are R mod P. Okay, proof. Okay, so what is the first module? The first module is just M1 mod M0, which is just M1, and that is R mod Pi. We are saying that should look like R mod Pi, R mod P1. So in other words, we are saying that there is a cyclic quotient module, quotient by a prime ideal that sits inside M. And we know one place to look for such a thing, which is an associated prime. Okay, so let P1 be an associated prime, and M1 equals then R mod P1 injects into M, call its image M1. Okay. Now we go modulo M1 and construct an M2. Now go modulo, now do the same thing, do the same in M mod M1 and get an M2 such that, M2 will get some module here with the same argument, look at its pre-image such that M1 is inside M2 and is inside M. Okay. And we can repeat this, to get a sequence M1, M2. This must stabilize, but the only place it can stabilize is at M, because if it stabilizes elsewhere, just go modulo that and do the same argument. Okay. So do this, and this stabilizes exactly at M. It cannot stabilize strictly inside M, because then you go modulo that stable value and then repeat the argument, and then you would have constructed one. Okay. So this is and often because this gives us sort of a inductive handle to answer many questions about modules by just looking at quotients by prime ideals. Okay. And we know that in some sense these might be easier to handle than arbitrary modules. Okay. So this is some proposition that will get used sometime later. Okay. So so I conclude this lecture with two examples. One example. The other one we already worked out, which was x squared comma xy. So this is an example. Let's do x squared. So now example 1. So R is k xy and I is x squared xy. We would like to determine its minimal and embedded components. Okay. So then we know that radical of I is x. So min of R mod I is the singleton x. Okay. And then we also saw that this ideal is associated to R mod I. We knew the irreducible and primary decomposition. So, okay. But how do we get the uniqueness? So we just found one. How do we know that it's unique? So how do we do that argument? So to find the component, the primary or irreducible component, for x, okay, we look at R localized at x. Okay. So we look at I, R localized at x. But localizing many elements outside x is not a very computationally convenient thing. So one we could do is we could just first invert y and then worry about inverting other things. Okay. But if you just invert y, so y is outside x. So in the process of inverting every element outside x, one step would be to invert y. Okay, so now what is this? So the ideal contains x squared and xy. In the ring Ry, y is a unit, so you don't need to put this unit. So xy and x will generate the same ideal after y is inverted. And once x is there, so maybe we can write this x squared xy extended to Ry. So I said this is unnecessary now in this ring. It's not going to change the ideal. So this is the same as so what I meant is this is a unit now in that ring. Okay, so this is the same as x squared x Ry, and of course if x is there then you don't need x squared, so this is x Ry. Okay, so therefore I Ry contracted to R is just x. Okay, so that is why the minimal component corresponding to this, remember this was just x intersect x squared y. Okay, so one can determine minimal components like this. This is a way to find them. Okay, we will do one more example which is a little bit more complicated. Okay. So R is the ring in 4 variables u, v, x, y, and I is the ideal generated by ux, vy and uy plus vx. Okay, so there are 2 sets of variables and then we are taking all 4 products, but except in the third term we are taking the sum. I mean we are taking 2 products separately and then taking the sum. Okay, so this is, then we would like to know what this is. So first we would like to understand the support of M, support of R mod I. Okay, so P contains I implies ux, u is in I, u is in P, or x is in P, and so this is from the first term, and v is in P or y is in P, just the first term. Okay, so suppose u is not there in P. Okay, so first of all there are now u comma v is a possibility. Okay, so we can write u comma, we can just explicitly check, enumerate them. U comma v, this term is there, this term is there, and this term is there. Similarly x comma y are both in support of R mod I. Okay, so this is there. Okay. Now we can ask, suppose u is not there. Okay. Suppose u is not there in P. P is some prime ideal. This is some prime ideal. Okay. If u is not there, then x must be there, and if x is there, then this term is there. So this implies that x is inside P. If x is inside P, then vx is inside P. This implies that uy is inside P. So what is what I'm saying here? X is inside P means that the second term here vx is inside P, which means that the first term is also inside P, but u is not there, so y is inside P. Okay, so in other words, x comma y is subset of P. Okay, similarly do for v not inside P, x not inside P, y not inside P. Okay, so the conclusion of all of this argument is that the minimal primes in the support of R mod I is just 2 things, u comma v and x comma y. Okay. Now we can ask what are the other associated primes, and if there are, what are they? So let's first evaluate the primary components corresponding to these primes. So what is the primary component. So we don't need to know the entire associated prime to determine the primary components for minimal primes. That is one advantage of that theorem. Primary component for u comma v. Primary component of I for u comma v. Well, we just localize it. So this is I r localized at u comma v, and then we want to contract it back to r. But again, localizing it, this is not that easy to, we don't even, it's not easy to describe that ring, but we could just start by inverting x and y first. Okay, so then, okay, so this is the same as, okay, so this is inverting everything outside u, the ideal generated by u and v. Okay, so when we invert just x and y, we already get u and v. If we invert x, then as we argued in the previous example, this becomes a unit, and then we just need to put in u. Similarly, y becomes a unit, so we just need to put in v. And once u and v are there, all the terms are there. So then we can just conclude that this is uv. Okay, and similarly, I r x y intersect r is xy. Okay. So these two are two primary components. Now we check, is I equal to uv intersect xy? Is this all the components that we have to worry about? So the answer is no, because the right hand side is ux vy and uy plus v, uy comma vx. Okay. There are four terms here, while in I it was just a sum. So that's a smaller ideal than this. Okay, so this is, the right hand side is no, which means that there are other associated primes and we need to find them. Okay. So what are the other associated primes? Okay, so let Q be an embedded prime, meaning a prime that's not minimal. We could just say let Q be any prime. Let Q be an associated prime. Okay, such that Q does not contain U. So we're going to do this. So which means that Q RU is associated to RU mod IRU. Okay, but what is RU mod IRU? So we will just invert U here, and if you invert U, we would get x, okay. And if you invert x, then it just becomes v and y, and so if you invert u, then u gets killed, and then if you invert y, v will get killed, and in R mod I, if you invert u, then x gets killed, and then so let's write this out. Okay, so RU is k adjoint u v x y and the inverse of u. Okay. IRU is ux vy uy plus vx. Okay, and so RU mod IRU, this is k u v x y u inverse modulo. So u is a unit, so we just need x. Okay, and u is a unit, so we can remove this. Y plus v, we can rewrite this as u inverse vx, okay, and vy. So what have I done? the first element you don't need the u because it's a unit, so the remaining things is only needed in the ideal. In this one, we use a unit, so I can multiply both sides by u inverse and rewrite this as y plus u inverse Vx. Okay. Now, in this ideal, we have u v x y u inverse modulo. There is x here, and if x is there, then one does not need this term, this second term here, because this is just a multiple of x. So one just needs y. And if one has x and y, one does not need this. I mean, one has y, one does not need this term. So this is just this. Okay. So in other words, but this is a domain. This has only one associated prime. Okay. So this is a domain. Okay. This is just killing x and y here. So it's just k u v u inverse. That is a domain. Has only one associated prime, which is this. So in other words, so this implies that if q is an associated prime of R mod I such that u is not inside q, then q is x comma y. That's what this conclusion, this argument says. Okay. So now we can, so we can do this for the remaining other variables also. Do this for the other variables. Do this for the other variables. Okay. Now what? So the conclusion would be that first of all, there is an associated prime which is not minimal, and it has to contain, if it doesn't contain u, it's a minimal prime. Similarly for v and x and y. So the conclusion is that associated primes of M minus the min of M is the singleton set which consists of all the variables. So let me just repeat how we got this. If you have an associated prime that doesn't contain u, then it must be this. If you have the same argument to say if you have associated prime that doesn't contain v, it must be this. Similarly, if you omit x and y, we will get u and v. If you localize x and localize y, we will get u and v. However, we know that there is an associated prime which is not minimal because the minimal components don't give I. It's something bigger than I. Therefore, there's only one solution to this problem now, that associated prime, there is an associated prime which has all the variables, and this is the maximal ideal. Okay. So therefore, associated primes is minimal primes plus this maximal ideal, minimal primes over I plus this maximal ideal. And now, how do we write a primary decomposition? Well, because this is a maximal ideal, we are lucky any ideal J such that radical of J is u v x y is u v x y primary. Okay. So now what do? Well, we play a little trick, which is that let J be equal to I plus u v x y to the k, where k is very large. Okay. So radical of J is, so J is u v x y primary, and then check that I is indeed the components for the minimal primes, which we have already worked out, and J. and it's independent of that exponent k for whenever it's very sufficiently large. Okay, so this is one example which sort of goes back and forth between various ideas that we learned and then lets us compute. Finally there is a trick, but apart from this trick here, everything else in one way or the other we have seen in earlier lectures. Okay, so this is the end of this lecture.